Hello, everybody. I'm excited to be with you today and excited for the three panelists that we're going to hear from. Now, this panel really focuses on the not silver bullet solutions, kind of like the management practices that farmers can do today that could optimize both their emissions and their productivity, and the systems that may allow them to do that and transform that into accountable reductions in emissions that matter for corporate commitments. So first, I'd like to welcome Dr. Mike van Amburgh. He is the professor in the Department of Animal Science at Cornell University, where he leads development of the Cornell net carbohydrate and protein system, a globally used model that helps farmers feed dairy and beef cattle more efficiently and with reduced environmental impact. His current research focuses on whole animal nitrogen metabolism and amino acid efficiency, supporting strategies that lower nitrogen inputs without sacrificing milk production. Mike?
Hi, everybody. I feel like at lunch I told somebody I'm either a unicorn or a zebra in this group. I'm not quite sure where I fit in, but that's okay. Let's go. Oops, maybe not. That's going the wrong way. Maybe I got to go backwards. That's not it either. Got my slides anywhere? Keep going. There we go. Okay. What a start. Okay, so I'm going to talk about environmental management from a dairy nutrition perspective in the CNCPS. We'll talk a little bit about what the CNCPS is, right? So I came to Cornell as this is going to give everybody my age. I came as a starting graduate student in 1989. How's that? Never left. Not really. I was offered a job at Davis. It just didn't work. But anyhow, I was on the first generation of what's known as the CNCPS. It's a computer model developed to predict dairy and beef cattle diets, nutrient requirements, right? So we use it to frame out the nutrient requirements of cows. And that's what my group is spending a lot of time on right now, is trying to figure out the nutrient requirements of these new modern genomic dairy cows. They have great capacity. I'm going to share that with you here in a little bit. Feed utilization, animal performance, nitrogen, phosphorus, and methane output, right? So the model was originally designed to feed all cows everywhere. It has a bunch of Bos indicus and Bos taurus cows described in it. Most of the time it's used for dairy, but it can be used for beef cattle, and it has been used around the world to do all of that, right? So it's not this kind of uniform dairy thing, but that's really where it gets its most use. Along the way, we decided that because of the environmental impact, we would start to frame the model out to be able to predict excretion. So the first thing we did is predict phosphorus excretion for the New York City watershed, so we could reduce that. And then we moved on to nitrogen, potassium, lots of other things. I'll talk about that. We built it to link to other models to have the right outputs. Some of that's been done, some of it haven't. It's based on accumulated knowledge about feed composition. We build some of our own feed analysis. I do feed chemistry as a hobby, just kidding. Digestion, metabolism, and supplying nutrients to meet those requirements, right? What does this thing do? Goals of improving it, right? So it's improving productivity, it's reducing resource use, and in the end, it's to protect the environment, right? Dairy farmers in the end, despite the fact that they're capitalists and they want to make money, are very cautious and very aware of their impact on the environment, especially in New York where I work because of the Finger Lakes and all the watersheds. We got multiple watersheds there. So nitrogen, phosphorus, things like that, they are very worried about. So we want to be worried about it with them, right? And we want to accurately predict the nutrient requirements, supply, and enable the nutritionist to identify what the source of the variation is, right? We're very interested in what's first limiting. If you can frame all this out, you can figure out what's limiting, then you can make an informed decision to increase productivity, reduce the environmental impact, whatever your objective might be, right? So, this one's easy, right? This is kind of the anti-methane talk. Not really. But there's nothing here about methane, but it is about productivity, right? Milk yield, milk fat, and protein yield, improving nutrient balance. And anything that we can do here is helpful, right? It requires some inputs, it requires some feed chemistry, things like that. Resource use, right? Optimize feed and feed costs. That's where we make money. Here's where I think we're having the most fun. Formulate the most efficient diet, get the greatest productivity per unit of input to reduce the carbon intensity. We are having a lot of fun around that concept, right? We're not just focused on methane, we're focused on carbon intensity. I'll give you some examples of that in a minute. Reduce overfeeding and excretion of nitrogen, phosphorus, potassium, and other minerals, right? There's a big need to do this. We have a major project right now in the state. New York has decided they want to reduce nitrogen excretion. Dairy farms look very good on phosphorus balance. We look out of balance on nitrogen. We have some money from the state to figure out how to reduce nitrogen excretion, right? We're in the third round of that. I'll show you some examples of the second round. What about where is this thing? I don't like software. So in 2005, we declared this an invention of the university so people could license it. And there's many companies that have licensed it. This is good and bad. It's good because it gets used. We have to approach this like a physician, do no harm at this point when we make an update. It has to work. We have to have tested it. It needs to be published because when it goes out, it's impacting a heck of a lot of cows and livelihoods, right? It's used to formulate diets for about 70% of the cows in North America right now. It's in over 40 countries. Somebody told me the other day it's over 60 countries, but I haven't updated the slide. There's thousands of users around the world, right? So one of the things, though, despite its broad use, it doesn't really generate a lot of income for maintenance and development, right? That's still a get on your knees and beg thing. But where do we see it? Okay, it's in its 7th generation. I got 2 minutes. Okay, just got to the fun stuff. It's in its 7th generation. We keep iterating on it. Our committee is the 550 cows at our research farm. They're brutally honest. When we do something, the cows agree, we can kind of check the box. When they disagree, that's when we go back to the drawing board and figure out why we couldn't get this all to work, right? So that's how we do this. What we're seeing with better diet, formulation increase in milk fat, composition and yield of 17.5%. Protein's tougher, we get maybe 8%. Overall, we're seeing 17 to 18% increases in energetic efficiency, which is like a 17% increase in productive use, in productivity using the same resources. That directly translates into a 17% decrease in methane intensity, right? So we've talked about intensity kind of roundabout here. That's exactly where we're operating right now. I'll give you some examples. A 10 to 12% reduction in nitrogen excretion, right? Enables Holsteins to produce milk like Jersey cattle, right? It's actually better than that. So we published this a long time ago. We think about the internal use of nitrogen, but practically, Laura from iFeeder said to me, is this practical? And I said, it's very practical. We predict urinary nitrogen excretion, fecal excretion, and milk. And what we want to do is we want to decrease this urinary nitrogen excretion because that solves the environmental problem, also makes it more efficient, makes the cow more efficient, and we don't have as much ammonia and nitrous oxide, right? And we have objectives for that. We run studies, we can predict that. We can predict productive nitrogen. We can predict urinary nitrogen with very high accuracy. This is all published. And we can look at that ratio of productive to urinary nitrogen. That's already a good number. We can make it better with better amino acid balancing, right? And this is good for the environment. There's a 4% increase in energetic efficiency, a 6% increase in nitrogen efficiency on an already highly productive study, right? There's this thing. So this was a low, what have I got? 18 seconds. Whew. Okay, I'll go over just a little bit. So this is one of those low nitrogen studies that we just finished. The diet at formulation was 13.98% true protein, about 14.5 to 14.7 on a crude basis. If anybody knows anything about diets, that's pretty low. Well, here's these cows, the pink diet. This is a NANDA study. They increased in intake. Milk yield was good. Energy corrected milk at 5.2. The whole treatment started at 4.6 fat. They all moved to 5.3. So butterfat went up, 4/10, 5/10, 6/10 of a point, 7/10, 8/10 of a point. And protein went up, productivity went up, MUNs went down. We can predict productive in urinary nitrogen. We can look at fecal productivity, right? Here's baby buffalo, right? That's her. Before we ran out of nitrogen in week 5, she had 9.4% butterfat. That's water buffalo territory, right? I told you jerseys, we skipped over the jerseys, went right for water buffalo. She had a pair that went to 10.2% butterfat. That's genetics. You guys kept saying genetics. This is genetics in action, right? You just got to know how to feed them to get them to do that, right? Intensity, right? Most cows, she was 9.5. Most cows are 14 grams per kilogram. It's a 30% reduction in energy-corrected milk, right? We work with other herds. This thing is used. Here's one of the herds in my neighborhood. 1,700 cow herd, 34,000 pound herd average about 5% fat when everything's working, 3.5 to 3.62 protein. Energy corrected milk is averaging over 159 pounds a day with a feed efficiency of 2.1. Here's one of those cows. She made 51,000 pounds, 2,000 of fat, 123 pounds of milk a day, right? What's fun about that is that we can formulate diets for those cows, right? And the model will resolve that. Not that every cow is going to be that way. The point is that we have this capacity to do some of this stuff. We need to seize that opportunity, right? Because that's how we're going to reduce impact, right? So nutritionists are the gatekeepers. The CNCPS is a gateway for the nutritionists. No technology will be used on a farm unless a nutritionist knows how to respond in the diet or can formulate around it. Any ingredient with non-nutritional characteristics will require more information for formulation other than a yes/no answer on seed mitigation. That is it.
Thank you, Mike. Next, we're going to have Dr. Juan Tricarico. Juan is the Senior Vice President of Environmental Research and Distinguished Scientist at Dairy Management, Inc. He's a recognized expert in enteric methane mitigation that collaborates across academia, industry, and government partners to advance environmental stewardship in the U.S. dairy sector. He holds a doctorate in animal science from the University of Kentucky and has over 2 decades of experience in agricultural sustainability. And with that, I'd like to welcome Juan.
Okay. Thank you very much. I do want to thank everybody for being here. I also want to thank, I believe there are people looking at us virtually, so here's a wave to you out there. I know it's much more difficult to continue paying attention when you're doing it virtually. Look at that. The slides worked for me. So, how many people in the room have heard of Rufus? That's good, Most people in the room have heard about it. I have been told that fewer than most know what the heck it is. So in the next few minutes, and with the use of 3 slides, I'm going to attempt to explain to you what is Rufus, what is its architecture, why is it different, and how is it made available for people to use. I'm going to use 3 slides, as I said. This first slide is going to be mostly about the modeling environment. I'm going to then use the second slide to talk about how it integrates existing science and develops new science. And then I'm going to finish talking about open source and how Rufus can be used. The most important point in this particular slide is the whole figure, the entire figure. Because Rufus is a modeling environment, right? And so I'm not going to talk about its features. I want you to walk away out of this room understanding the concepts behind it. If this presentation or presentation is not enough, there's a poster out there, and I'll be glad to walk you through the poster as well. Most important part is that Rufus is driven by inputs, just like any modeling exercise. And those inputs are run through, in this particular case, 4 different modules. Those modules are the animal, the manure, the soils and crops, and the storage module. According to our director of software engineering, Rufus takes in 2,000 inputs and creates 11,000 outputs. That means that in order to deal with all that level of information, you also need to have systems that allow you to summarize and eventually bring all that information in such a way that it can be scaled and it can produce meaningful outputs that can be used for analysis. That was the number one thing I wanted you to walk away from this slide. It's about a whole farm system. And it is, again, the integration. It's everything. These are not separate tools, although it is modular, which means that these pieces can change without breaking the entire system. The second piece that I want you to pay attention to, which is a key differentiator in Rufus, is that this system goes through a flow of mass and materials through the whole system daily. Today, it runs on a daily time step. Wonderful. So let's talk about integrating established models and extending the science, which is basically about not inventing or reinventing the wheel when it's already there. So, as I already mentioned, the 4 modules are what you see on your left-hand side, and they run on a daily time step. So that means that every day, mass and nutrients flow through this simulation. But in essence, another key differentiator about Rufus is that it actually integrates established models. And so I have here listed a few examples. I'm actually not going to read them because I don't have time, and you can read quicker than I can talk. But I'm sure you recognize the name of some of those models that are integrated into the Rufus modules. There are, however, some areas where there was no model that existed, and therefore new science had to be developed. And that's what you see on the other box closer to your right-hand side. It says newly developed components. Again, these are examples, but I'm going to focus on one of them in particular, which is the animal life cycle model, because again, it's a differentiator for Rufus. It actually simulates each animal individually on a daily basis and stochastically across the different life stages of the animals. This is really important and it's a key differentiator because it allows the incorporation of events into this type of situation. And that's where the stochasticity comes in. A dairy cow can get sick. It has a probability of getting sick. Or a dairy cow has a probability of getting pregnant, and so on and so forth. Rufus handles that. He's able to handle it because its architecture, the architectural choices were made in order for it to be able to do that. Now, of course, this is a challenge and an opportunity. It's an opportunity because in a certain sense, it allows for simulating the messiness that happens on a dairy farm on a daily basis. Of course, this is too much to deal with on a daily basis as well. And therefore, what you need is a whole layer of tools that allow you to synthesize the information, which is at the bottom. It's also an opportunity because it gives you information and you need many runs. So you can actually look at distributions of events. You can look at distributions of outcomes instead of looking at a single number. Now, as I mentioned, there are some elements, some modeling capabilities that needed to be developed that are environment level. And these are the data harmonization layer, the output manager, and the uncertainty analysis tools. These are software capabilities that were needed in order to make the integration work. So these are tools that were developed that are embedded within Rufus. So I'll give you just one example, as I mentioned before. When you have 2,000 inputs and 11,000 outputs, you're going to have to use something like an output manager in order to create customized reports that address what you specifically are interested in, because there's way too much information, in fact, information that you may not even want to look at. So to finalize this presentation, I want to show you this last slide and talk about the open source nature of Rufus. I'm not going to spend too much time on this one because everything is written here on the slide itself. And as I already said, you can read it quicker than I can speak about it. Important point is that openness is about everything being publicly available. The source code, scientific documents, the manuals, even the governance is available. On GitHub, it's the public repository where everything lives. It's also written in Python using solid design codes, which is an acronym used by software engineers. I'm not going to go down that road. It does have some specific rules of engagement, though. One of those are the licenses, and you can see right there. We use GPL version 3 license, and it means that it's open, there's an opportunity for expanding, there's an opportunity for connection, but there are also some basic rules of engagement that need to be followed. They're all up on the Git repository, and they're accessible to everybody that knows how to read English. Finally, I'm going to say a few words about the potential uses. Because it is so flexible, it has an opportunity to be used in many, many different ways. I only listed a few. For example, to evaluate management strategies. Because again, you simulate over the course of whatever period you want, and you simulate many times, and then you can incorporate all that information to understand what are the probabilities of nutrients being translated into milk, used for production of milk, or materials that end up in gas, like greenhouse gases, or in excretion. You can therefore quantify environmental outcomes. You can conduct scenario analysis. It's actually itself a computational laboratory. And it can also be used to support extension education and other types of collaborative development engagements. With that, I want to mention that if you're interested, my last line for this is go and see it. It's in the GitHub repository. It's written down there on the slide. But I do have these little nice green cards that have a QR code that will take you directly to the GitHub repository. So if you're interested, you can see me afterwards, and I'll gladly give you one of these cards that I had asked to get made so that I can give them to you. So I don't want to take them home. You come and you pick them up. Thank you.
Our final panelist is Jim Eckberg. Dr. Jim Eckberg is Director of Science and Innovation at the Edge Dairy Farmer Cooperative, where he leads sustainability program offerings for member farmers focused on conservation, environmental management, and industrial sustainability goals. He previously served as Senior Research Scientist at General Mills, advancing dairy sustainability, water quality, and biodiversity across the company's supply chains. He holds a PhD in Applied Plant Sciences from the University of Minnesota. Jim, welcome to the stage.
Well, I have to say that as I got here yesterday, and the longer I stood in the audience, the more and more I started to get nervous and intimidated by the incredible programs that we have represented in the room. Some flashbacks to my oral exams and responding to questions from my my advisors and committee. Kind of, I have to say we're all part of that too. But the clicker is right here. So that being said, I think there continues to be a gap between the programs and the science that's being developed and the farm community and the rest of the value chain, and addressing that in whole farm and farmer-led approaches are what I'd love to talk about here. This work really wouldn't be possible without getting to the slides. Let's see here. Is it that way? All right, great. That was on me. I went up. But this work really wouldn't be possible without our farm members first. And I work for the Voice of Milk. The Voice of Milk is a consortium of 4 organizations. It includes our commercial side, which is the Edge Dairy Farmer Cooperative, which recently moved into the second position in the country for the largest cooperative on volume. Our over 700, close to 800 farm members produced about 17 billion pounds of milk last year. We are a verification cooperative, so when you ever see a line for a private farm shipping milk, we are representing those farmers. So we don't hold the physical assets like a public cooperative, but we work with those farms that are direct shipping into the processor. So this provides some nice advantages for traceability and collaboration between our processors and our farm members. We represent 32 processors in our whole network of varied size. So that's the commercial side. We also have Farmers for Sustainable Food, which is a nonprofit. This is a part of the Voice of Milk. So as we're supporting farmers on the commercial side of things, we're supporting them with the adoption of conservation practices. And a lot of our on-the-ground activity is focused in Wisconsin with producer-led watershed groups, also now Minnesota with producer-led watershed groups. And this is a expanding, I should say rapidly expanding model for farmer-to-farmer networking and peer learning. But I think that we have a lot more work to do to get farmer-led innovation advanced into these climate initiatives, and I can talk a little more about that. I just have 3 slides. And then last but not least, the other 2 organizations are policy advocacy groups, the Dairy Business Association in Wisconsin and Minnesota Milk Producers Association, both of which advocate on behalf of dairies for sound and scientifically robust regulatory policies, as you can imagine, largely around focusing a lot on issues of water quality for permitted dairies. So this talk, the 8 or so minutes I have left, is about how do we connect the value chain to work on these practices and adoption of practices. So many things that you've heard about today. How do we work on this in a way that's whole farm, that's holistic, that's farmer-led, then actually delivers reductions, greenhouse gas reductions for the full value chain? And this is really done in service to recognize and continue to support farmers with incentives to continue to make improvements in efficiencies. And this is about also supporting the whole value chain and really keeping milk relevant, because reducing emissions ultimately comes down to, I think, consumer trust, and supporting this is a really important part of our diet and a really important part of protein and nutrition. So let's first talk about farmer-led. We've heard phrases like farmer-led, farmer first. If we were to look in the literature, I think what you probably would find that's most relevant is participatory modeling approaches. And that is the direction that, with the support of PACT and our work with our farm members, that we're moving in this direction. This idea that technology is just linearly developed and then delivered to the farm is not necessarily something that we can apply on a farm-by-farm basis when we're talking about whole farm management. Because though, genetic selection, which I'm so excited about and thinking about this in a whole farm, a holistic modeling approach, is one of the key solutions. How does the farmer use that information to change decisions on the farm? And establishing that is critical to evaluating a baseline or a counterfactual for us to be able to quantify, inset reduction, a reduction in metric ton CO2e. So there are countless examples, too, of other ways in which we have to take these solutions and really work with the farmers to apply them in ways that are adapted on their farm. You maybe have heard about this idea of, well, let's just keep our cows longer because this carbon debt from raising a heifer is problematic. So if we just keep the cows longer, right, that'll reduce emissions. Well, that really depends on the context of the farm. It depends on the emissions of a replacement. It depends on how well the milk yield can be maintained in those later lactations. And obviously, you have to consider that meat to milk allocation too, because in shifting that, you'll be shifting and reducing how much meat is being exported as you export more and more calves from the farm instead of culled cows. And so evaluating this as a farmer-led, I hope you're seeing is bleeding perfectly into thinking about whole farm modeling approaches, and whole farm modeling approaches that generate insets to substantiate that reductions in GHG have happened, but also report on emission factors so that the value chain can continue to show progress towards improved inventory accounting, I think really go hand in hand. You probably heard about a lot of the limitations and the challenges that CPGs are up against with reporting on improved inventory accounting, and there is, 1 minute left. Is that okay? In their footprints, and those are real. Okay, so we have to think, I think, a little more creatively as an industry around ideas of free allocation, because CPGs are not necessarily buying pounds of milk; they're often buying ingredients of milk, right? So those early adopters have some flexibility. And I'll direct to the Bound Dairy program, and Jesse Delo's program is an outstanding example on free allocation. But as CPGs are also transitioning to work on reducing their footprint, it's also about showing and substantiating that reductions have actually happened. And that's where I think insetting in combination with emission factors really comes in as a dual ledger, or something that has to happen simultaneously. In the context of a whole farm model, we are able to actually inset reductions resulting from the implementation of a suite of practices that are implemented simultaneously. And the work that I did when I was at General Mills was with a group out of Quebec called Logiag. They're a group of modelers, scientists, and protocol developers. And we built a whole farm insetting methodology based on Quebec dairy. We validated it with Sustain Cert at the end of 2024. It delivered its first verified impact units last summer. It's on target to reduce its next round of impact units. And this took a whole farm approach to reducing emissions by considering the unique challenges that dairies are facing when they're under supply management, that context, and looked at simultaneous improvements to herd management, changes in culling rates, in that case, reductions in culling rates, increases in nutrient use efficiency, greater use of ration and legumes integrated into hay. Again, an option that you've probably seen in Quebec, but perhaps not in other geographies. And under review right now is our first manuscript from this group, which is the whole farm scenarios informed by 30 dairies. And we'll see if that's accepted. So last, I'd like to just end by saying that all this work really has to happen in a public to private partnership. I think the most credible solutions are the ones that are not developed as a black box, but ones in which the competition and getting, working commercially is really going to come from how quickly can you develop these holistic approaches with the farmers that you support and have that reflect farmer-led innovation. The tools that we work on should really be common source. And that's why with support from PACT and a continued advancement of this work, we'll be working to publish on the methodology for whole farm insetting. And we're really excited to work with technology service providers on how can we integrate a lot of the great approaches that you've been hearing about today, which I think are going to put us on a path to working towards net zero.
All right, if all the panelists would come on the stage for question and answer. All right, thank you all for presenting. A question, so we see the incredible complexity it takes to model cows. And at the same time, for people making decisions or corporations, including changes in their inventory, they need something easy to action on, which means clear and concise. So how should we think about the process of boiling down all of that complexity into simple advice? What makes that possible so that farmers and corporations can take actions? And I'll send that to Juan first.
Thank you, Doc, for that question. It's a great question. So if you think about it, Mike was talking about CNCPS, which gives a level of sophistication that it's very high, and nutritionists would use it to achieve the types of things that he was showing us. Cows achieving unbelievable output, but that's really not what's required. All the way over here by Jim, in terms of being able to report. So there is definitely an element of translation that needs to happen. There's definitely a need to identify the essence of what needs to be captured and translated into something that's going to be meaningful. I don't have a specific answer, but it is an important gap, an important challenge to understand, right? And I think that there's no really stopping how science is going to keep on moving forward, right?
Yeah.
So that's going to keep on going, is trying to figure out what are the pieces of information that are truly essential, that it's not too much detail, nor it is a simplification that basically misinterprets what's really going on. So it's that sweet spot in the middle that we'll have to find out.
And so to add on to that, drawing on a question from the audience, and this one will be to Jim. So, to put data into this model, you need a lot of data, and the more data you get, the more work that can be for the farmer, as well as the more concerns that the farmer can have about their privacy. So how do you think about balancing the need to get that data with both the farmer privacy concerns and minimizing the burden on farmers for participation in these programs?
I think we need to flip the script with the farms, because the question is not, I need this data next and I need this. It's what do we need this data for? And so with our approach to our farms, it's about articulating, we want to add value to milk and being able to evaluate environmental metrics, greenhouse gas being one, but there's water quality and other metrics, is about bringing more value to your farm to make sure then once we are aligned that our goal is really about creating market opportunities. Then the next question is, well, what's the bare minimum amount of data we need to establish a baseline and then to be able to evaluate an intervention that you have made a change and here's the quantified reduction. So I think farms a lot of our members are aggressive and eager to explore this, and it has their whole farm, which is complex, has to be boiled down into some of these simple metrics that can be reported to the value chain and have clear expectations with the members on that process as it goes.
Great. Mike, this next question is for you. So it's how low can you go in crude protein in the diet? You showed with your amino acid feeding this 17%, this very impressive cow, baby buffalo.
That's what we named her. Yeah.
So, but how much further? How much more room is there beyond that?
So, in complete disclosure, I hate the term crude protein. It's my objective to get away from that because it doesn't describe anything for a cow, right? The cow has two requirements. She has a ruminal requirement for nitrogen, which in our modeling efforts we have separated. And then once you get out of the rumen, once you get past the microbial ecology or community, she has an amino acid requirement just like a pig or a chicken or anything else, right? And if you separate those two things out, the cow is actually more efficient with her amino acid use than a chicken or a pig, right? It's the rumen that confuses everything because there's all this non-protein nitrogen that those bacteria need, all the ammonia and things like that. How low can you go? Probably about 13.5 is what we think would be we ran out of nitrogen.
Yeah.
Right. What I couldn't show you, right, because that's a whole talk in itself. Our whole purpose is to find the bottom, those cows, but we build the best diets we can, right? because we want the cows to be as productive as they most possibly can be while we're trying to find that bottom threshold. And they all, if I could show you the graph, they kept increasing in milk fat and milk components without changing milk yield until week 5. And then all of a sudden in week 5, they started to say, hey, we ran out of nitrogen here, buddy. Which is where we wanted to be. It made everybody sad, right? Because we went, the enzyme system said, sorry, I don't have enough to go, and we're going to drop in milk fat and protein. But it's probably somewhere around there, the quick answer.
Great. Next one is for Juan, which is a combination of 2 questions. Where is Rufus being practically used today? And to what degree is it transferable outside of North American dairy systems?
Yeah, that's a great question. So, in theory, it is transferable outside the United States. It is built with a lot of United States-based information at the moment, right? So the benefit of this is that anybody that has information that is applicable can go see how it would fit, and then they can go ahead and go through the systems, the rules of engagement, in order to incorporate that. They can fork it or branch it. Those are the kinds of things that happen in this type of open source model. So the point of the matter is that it's out there for people to play with. Right now, Rufus does not have any type of interface that is the type of interface that people are used to seeing, particularly non-software engineers, right? So in order for anybody here in this room to run Rufus, you have to get all the code, bring it onto your computer, and then you need to install some elements relative to Python, and you run it out of a Python command line. Okay, it's kind of like for those of us that have been around for a while, where like you were saying, if you remember that movie War Games or something like that, where the guy was typing on the computer, and it's all text based. That's how it runs at the moment, right? So primarily the people that are running it are people that know Python and know how to deal with command lines at the moment. Eventually that may change, particularly because, again, it's open source. People can build interfaces for it if you are so inclined.
Great. Jim, this next one is for you, which is, you've talked a lot about insets. Have any corporations actually created insets using these kind of models, or is that a thing we should expect in the future?
Yeah, this work was based on the Dedicated Dairy Farms program, which was validated by SustainCert in December of 2024. And if you're familiar with these processes, these auditing processes, and you'll know that verification and validation often are working in tandem. And that initial group of farms produce their first collection of metric ton CO2e or impact units. And so the answer is yes, it has gone through that first round. That was in July of 2025. And there's certainly a lag between reporting and actual improvements that are being made. But yeah, that program now has 100 dairies on it in Quebec. And our work with Edge Dairy Farmer Cooperative is about taking these tools that have been developed with the support from General Mills and adapting this to U.S. dairy and U.S. dairy models, and especially working with our farmers in a cooperative or participatory approach to identify what our priorities are, for advancing these whole farm modeling tools.
And that's Bell cheese, so the little red pucks you can get wrapped in wax.
In Quebec, or yeah. Well, I'm not familiar with the different brands up there, but yeah, I'm aware of Bell, and I should say General Mills had Liberté. They were formerly the owner of that prior to that divestiture. So
great. Now I'd like to turn the conversation to genetics a little bit, starting with Mike, which is, how do you think about updating CNPS as the genetics evolve, right? Will it continue to be accurate? Like how do you wrap your brain around this constantly changing genetics background that you're working in?
Yeah, that's the cautionary tale for all of us, by the way, because I'm a little conflicted on the idea that we want to try to simplify some of this stuff, that the simplification may be looking backwards. It's kind of like looking at your belly button, trying to solve a problem out there, right? Because these cows, just if you're talking about Holsteins and Jerseys, they're changing and they're changing rapidly, right? If you look at the paper from 2022, since genomics, milk has increased 79%. Fat has increased 151%. Protein has increased 192%, right? I gave you some evidence of those cows just in our own herd, right? So once you know how to feed them, they're very capable of telling us what they can do. What do we have to do? It's very complicated. I have to wrestle my way into Joe's chambers. Because what we need is some chamber data where we've actually looked at their efficiency of it's not on milk volume. This is going to sound funny. This is all on components. It's the efficiency of partitioning the components, right? The energy system was designed in the late 50s, 60s, and 70s when we didn't have cows like this. If you look at the capacity of these cows, it's really the big change has been on components. They don't change their dry matter intake as much as you think they would or could. They just partition more to the mammary gland. That's an efficiency that we don't know how to capture. There's no model on the planet that if you balance for amino acids that will tell you this is what you should expect, right? We're having to do that by inference and back our way into those calculations. We have the partial efficiencies all worked out. Our latest version of the model is framed to do it, but we need to get some chamber data.
Yeah.
And a few more amino acids.
And I have a related question for Juan, which is Rufus models the individual animals rather than the herd. But does that have implications for its ability to model low methane genetics?
Yeah, so there is actually a Rufus genetics model that is under development. So it's not yet incorporated into the version that's on GitHub. Eventually, it will get there. Actually, if you want to learn more about it and you're attending ADSA, I believe there are at least 1 or 2 presentations relative to that. Basically, the reason why you can handle that is because as you're modeling individual cows, you're able to also define new class variables or characteristics for the cow, and therefore you can attach a cow-dependent element. And in this case, it's actually the genetic merit of these cows, that goes in there and gets modeled. So the system actually will be able to handle eventually when all of this gets incorporated, not only the type of genetic merit that an event as a calf birth occurs in Rufus in this simulated farm, but also it can look into the future with the current trend, like you're mentioning, Mike. With the current trend, how genetic merit is going to change into the future. So those are the kind of concepts that individual cow simulation allows you to do.
The next question is for the floor, so anyone here can take it. So we've talked in this panel about dairy systems. Obviously, beef is important in a larger portion of greenhouse gas emissions in agriculture. What aspects of these initiatives are potentially transferable to beef systems?
I'll go ahead and start very quickly to get it off. So Rufus is currently dairy focused,
yeah,
right? But that doesn't mean that it can't be made into a beef focus for those users that would like to do so. The challenge is that you got to get the resources. You got to get a group of people. You got to get the financial resources, and in many cases, of course, you need that basic data. Like I show you, it's about integrating existing data. So if there is sufficient beef data available, sufficient science to integrate, then you already have a good place to start with this framework or this architecture. But right now, it's not there.
Let me push a little bit on that, Juan, because I know Rufus doesn't include a pasture module. It's not grazing. Is it more? Are you thinking here in terms of like feedlot systems, or is there a path?
Well, what I'm saying is that the architecture of Rufus gives you the opportunity to model anything you want. The challenge is that to model something, you need to have basic data first. If not, it's made up stuff, right?
Yeah.
You need to ground it on something. So the opportunities exist. The challenge is you have to get a group of people that focus on that with resources to actually make it happen. Now, there are some opportunities. For example, as you brought the example there, Doc, of a grazing module. I mean, when a grazing module gets developed, it could be the basis for both a dairy or a beef application, right? Potentially, that's the thought process that could go into it, right? So there are opportunities for developing some elements that could do double duty and actually be used in both types of systems. Right now, because of the type of focus that has been placed, the type of effort, the type of resources that have been deployed against objectives in Rufus, it's, dairy focused.
Right. Jim, I think you had some thoughts.
Yeah, I think that there's an incredible partnership opportunity between dairy and beef. It would be a shame, let's put it this way, if we were to find ourselves in a situation of having stranded assets where reductions for a feeder leaving a dairy is there's no means to account for that in the footprint of a ranch. But a dairy's scope 1 essentially becomes the ranch's scope 3. So with a couple of recent papers that have come out looking at the beef on dairy footprint, I think those are relevant, and I think this is a key area for us to work on as a means to optimize that herd management and herd management decisions. How long should we be keeping cows? Depends on the dairy. It also depends on what semen are we using and what market opportunities are there. So the dairy herd, to Mike's point, is changing in many ways. It's aging, as we all know right now in this particular situation. And one last point, kind of I'll say, building on what you're saying, Mike, is that your work is the leading edge of this, and the scope 3 accounting is really trying to catch up. I'll add that it's also trying to catch up to the innovation of the farmers, and the combination of the research and what the farmers are doing, I think, is where we have a lot to learn in the GHG accounting space.
Yeah, just to add to that, I think that's one of I did beef work in my early part of my career. The whole thing has changed, right? Because as the beef population shrinks, just in the U.S. market, North American market, right? We're producing a heck of a lot more calves now. It is not the cow-calf operation of our grandfathers, right? We're controlling the calves from day one. We're moving them where they're expensive. I think the whole model is going to change, right? And that may give us some opportunity to figure out how do we make it more efficient? How do we grow them faster? Kill them faster, right? So that we don't have as much time. All that, I think, is a possibility right now.
So, Mike, this is for you. So the nutrition that you can provide to an animal depends on the feed ingredients you can access economically. Does that limit any of the scalability of your approaches? Are there things you'd like to see developed on the feed ingredient side that you think would open up more?
Whose question is that? I can guess. Yeah. Here's where. So I think I'll say this in this audience, and it might be lost on some of you, but I think the dairy industry has hit the swine era, right? If you know anything about growing a pig, those pigs are fed a lot of crystalline amino acids to meet their requirements, right? And it's all built into the requirements in every genotype. They increase it every year, 2% on lysine for the lactating sow. The cow, Kurt Van Tassel tells me that every calf born today is a new genotype because of genomics, right? That's a really shocking statement, right? What it means is our amino acid requirements are going to keep increasing on a yearly basis, just like the pig. And we don't have enough rumen protected amino acids to meet all the requirements, which is why if anybody pays attention to markets, our fats here, right, and keeps changing, and our proteins down here, and we can't really move it because we don't have enough isoleucine, enough valine, enough leucine, enough arginine, and proline to make casein, right? So if you want to change milk composition right now, we need those amino acids. I can tell you the quantities. We've modeled that. We are very comfortable with the numbers. They're just not available unless you feed a 24% crude protein diet, which is what none of us are going to do, right? So that's where we're stuck. Yeah, so it's a resource allocation issue. There's an opportunity. I talked to all the people who make these things. They're all kind of looking at me like, yeah, I'm not sure. So we'll see.
All right, we have a few minutes left, so I'll have one last question. And this is, I think, for either Jim or Juan or both, which is, we've talked a lot about these as models of cattle productivity, as models of emissions, but of course, models of finance are extremely important. And we know, for example, that input prices change day to day. How do you think about that? The importance of that, has that been integrated in? Is that on roadmap to integrate in? Love to hear what your thoughts on
I'll
it.
go first again, Jim, yeah. So in the case of Rufus, there is an economic layer that is under construction, that it's 95% of the way there. So in the next version release, it should be incorporated. That's going to make a difference because then you're going to be able to evaluate economic outcomes on a post-simulation basis. So it's not going to run embedded like the 4 modules. It's an actual analysis layer that was like on the bottom of that slide that I showed, if that makes sense.
Yeah.
A lot of our farms, they know their numbers. They have a sense as to how different options will play out. For us, we're trying to show them what will be the change in emissions on their farm when they make those different choices. The value then is in generating insets and improving emission factor for the value chain. Our approach right now is in creating and setting this up so that there is a monetizable system, and it is based around farmer-led innovation. Having insets combined with emission factor, I think, gives a lot of clarity around this question of what emission factors should have premiums, and how do you apply that across different, really different production regions where emission factors can vary naturally or vary with environment. Having insets combined with that can substantiate those reductions for the value chain, show causation or what we call additionality, and then also provide monetizable units, all while keeping the reductions within the value chain.
Great. Well, I'd like to thank our 3 wonderful panelists, and thank you, the audience, for listening to us all.